Okay, thank you very much. I would like to say thank you to the program chair for allowing me to shift and reschedule my talk. And I'm sorry for the inconveniences that this may have caused to you. So my talk is entitled, as the session chair already said, Detecting Flawed Masking Schemes. So I will give a very brief introduction to masking schemes. So the context is well, side channel attacks, right? So masking is a countermeasure, it's a very generic countermeasure for DPA, for side channel attacks that use, for example, the instantaneous power consumption or the electromagnetic emanations coming from a chip that is executing your crypto to break the implementation. So masking is very broad, and you can apply masking to many stages of your design. But the core idea is to split your secrets. So, for example, let's say you have a secret bit B. With masking, what you do is you split probabilistically that bit into two shares. For example, B1 and B2. For example, B1 you choose at random, and then B2 you compute such that both shares sum to B. And then you handle them, let's say, independently. So you can see that this buys you some security because, well, even if you give an adversary any of the two shares, he will learn nothing about the underlying secret B. You would have to give both shares, information about both shares, in order for the adversary to learn something about B, right? So you can intuitively think that, well, if your device is handling each share at a different point in time, and you are analyzing the power traces time sample by time sample, then, well, looking at any time sample of your power trace will not tell you anything about the underlying secrets. So until now, this was all about representation. So this is about representing in a funny way all your secrets. This you would have to apply to all the secrets and intermediates of your algorithm. And of course, the most difficult part, let's say, is to compute on this representation, right? To do something useful while still preserving this shared representation. And that's exactly what a masking scheme provides you. So it gives you a recipe, an instruction procedure on how to compute your AES, your RSA, or whatever crypto in this shared way, okay? So this is, in a nutshell, what masking is. And it turns out that it's not as easy as it sounds. Although the splitting is very easy, maybe to compute linear functions is very easy, but well, the problem comes with nonlinear functions, and then yeah, designing computation procedures for this is not as trivial as it sounds. We will see this later. We will elaborate on this later. So masking is normally quite hard to implement, either in software or in hardware. It's quite delicate. It's possible that to implement a provably secure masking scheme in a completely insecure way. So even though the scheme is theoretically secure, it's possible to screw in many places. But also, it's possible that the masking is structurally flawed, that by the definition of the masking scheme, there are flaws that may be exploitable or not. So this is what we are going to focus on this paper. So we are going to focus on some masking schemes that they are structurally flawed, that as in the paper they are already flawed. And this is especially the case for higher order masking schemes. So this situation becomes more problematic in the higher order scenario. So there are many examples of masking schemes that, well, they are published and some years later they get broken. For example, well, I am going to put just a few lists. It's not meant to be comprehensive or complete, but it's just to give you a first overview of how often they get broken and how quickly they can get broken. So Kai Scham and Christoph Parr published at CTRSA a method to perform a table lookup, supposedly providing higher order security. And they gave examples for AES. And, well, their scheme was broken 1 year later by the authors, by Jean-Sébastien Corion, Emmanuel Plouffe, and Mathilde Rivard. And there are many other examples. Somebody presented at CHES 2006 a supposedly provable secure masking scheme that later got broken 2 years later at CHES 2008. This method was based on the FFT, if I remember correctly, and well, it has a first order flow in some variable of the algorithm. Some other authors published another probably secure higher order masking scheme in just 2010, and then almost the same group of authors broke the same scheme in FSC 2013. Now, this is an academic attack. This is not really something that would threaten the security of this scheme, which is really nice, by the way. They give a higher order construction for the AES, and it's based on the ISW algorithm of Crypto 2003, if I remember correctly. So this is really nice scheme, but well, it got broken some years later. It's still a higher order attack, so it's not completely broken, but this gives you, well, this gives you the impression that maybe something that is advertised as probably secure, maybe it's not that. There are many other schemes that get broken. For example, something proposed in 2012 that got broken in 2014, and also for hardware, there was some proposal in 2014 of a masking scheme mainly designed for hardware implementations that got later refined, let's say 1 year later. So if you look at those papers, at these kind of papers, they look really complicated, and they are complicated, especially in the probability arguments. Something like this. So this is a screenshot from one of the papers. And what is common in all these papers is that the main observation, for me, it seems to fall from the sky. Like, and then they elaborate, through a very complex probability argument, well, that they will justify that some set of variables is not distributed as it should be. But they don't tell you how, for example, they figured out that those variables are not distributed as they should be. They spend most of the paper trying to prove you that, trying to prove the claim distribution of those variables, so that you can reproduce the flow, but it's not very helpful, for example, if you have to design a new masking scheme, because those papers are very tailored towards specific masking schemes. So this is not something that you can really learn to later analyze a masking scheme. So that's my starting point of this paper. And actually, the tool that I propose here is something that will tell you which variables are not distributed as they should be, so that later, well, maybe you can write such a proof, or you can just move on and modify the algorithm so that you don't have those biases. So the principle of operation is very easy. It's based on leakage detection tests. So a leakage detection test, we perform that in simulation, and basically test if some variables are distributed equally for different secret values. Or, well, if you are testing for first order security, then you would have to look at means, if they have secret independent means. And well, I will not explain how to test this with a statistical test, because you all know better than me how to do this. But well, the result of this test is some statistic, and then you have to compare that against a predefined threshold. So here you have the run of a leakage detection test against a masking scheme that will fail the test, so is deemed insecure. So it's based on simulation, so it's based on simulating a bunch of traces. So for example, like 10,000, 100,000, 1 million traces. And you can see that for each number of traces, you do some computation, and then you take some statistic, and then you compare against a threshold. For example, here is plot this t value of 4.5. And then if the statistic surpasses that threshold, then it's deemed to be insecure because it has different means. Otherwise, it's deemed secure. So I plot here different test values for different pairs of secrets. And you can see that for many pairs of secrets, the means are different. So that's against the security claims of those masking schemes. So you can see also that as you have more traces, so as you spend more time simulating, you have more confidence in your results. So you are more confident that those biases are not statistical artifacts, but are actually there. And yeah, well, this is the situation for a masking scheme that would fail the test, and this is the situation for a masking scheme that would pass this test, right? So, of course, you are still not 100% sure, because maybe if you throw more traces to the test, if you were going to simulate this with 1 trillion traces or whatever, maybe the statistical test will tell you that there is some bias, but that's not really worrying for an attack that is bounded, let's say, by 1 million traces. Okay. So this shows you the statistical nature of this tool. And I will elaborate on that later. So this leakage detection thing is nothing new. It's something that is out there since already 2000. So probably like 1 year after DPA was introduced, was published, let's say. And it's introduced in a very nice paper by Coron, Nakash, and Kocher. And yeah, it recently got a little bit of more of interest, but I see this not very often cited. So that's why I wanted to put it here. So this is one example of how the tool looks like. So here I just write some code that describes the masking scheme. So this is the input for the tool. So I am just writing C for this masking scheme. So this masking scheme is essentially Reparaz 2010. So this is some refreshing block. So this performs a refreshing of your sharings. And this is the beginning of GF2-to-date multiplication. So you take some input shares, A and B, and computes the multiplication while doing some cross products. And well, the input of the tool is standard C code that you could run. Now the tool instruments this code and figures out which variables are being handled, and then performs a leakage detection test on those variables. So if you compile everything, well, you can see that it begins simulating with traces, and as soon as there is some bias detected, then it will tell you which variables or which lines, between which lines there is some high-order leakage. Okay, so this will tell you that there is something between line 74 and line 20, and that's between one variable that is living in the refreshing block and one variable that is living in the multiplication block. Okay, so this is the input-output interface of this small tool. Okay, this picture reminds me to tell you two things. So, as you saw, the output of this tool is not a hard proof. It's not something that you can. It's just it's just a statistical hint that there is something going on that is not as it should be. So many papers in this field are based on proofs, and well, I think already in the invited talk, somebody mentioned on the uneasy relation between math and crypto, and there are many papers that present proofs that later get broken. So our tool does not follow that approach. It does not output a proof, but just does statistics to figure out if there is something that may be harmful or not. And the second thing is we do many, let's say, dirty engineering tricks in this tool that are described in the paper. And one of them, for example, is scaling down the masking scheme. So this lady is testing a plane and is testing a scaled down version of that plane, where she can well, measure some things and try to extrapolate those results to an actual plane. So we do something like that. We don't work with normally we don't work with full-size block ciphers, but we work with striped down versions of them so that biases exhibit earlier, and we need less time to perform those tests. There are many other tricks that, well, they are explained in the paper. So also in the paper we write on some results that we got from this tool. So we reproduce the flaws that some other people found, right? So we implemented a bunch of masking schemes and ran them through a tool and discovered, rediscovered what was already known. And we also point out a flaw in the old scheme of Schramm-Parr when using funny S-boxes. And we also show second and third order attacks. So, sorry, attacks, no, leakage detection tests, so flaws. So these are two pictures of second order leakage detection on some higher order threshold implementations. Well, you can see, so this is a matrix of cells, and well, the color, so this is time sample, this is time as the execution of the this is clock cycles actually, and this is also clock cycles, so times flows from this upper left corner to this lower right corner, and well, green pixel here tells you that there is no leakage detected between the corresponding pair of time samples, and a red pixel will tell you that there is some leakage detected between those pair of time samples. So you can see that in this particular case, in this particular construction, almost all time sample pairs exhibit some leakage, okay? And the difference between those two pictures is, well, you can see as the confidence. So here, those are the points that we are really confident that there is some leakage, or number of traces. So if you have few traces, then you will get a picture like this. And if you continue cranking and providing more traces, then you will get a picture like that, okay? So the details are explained in the paper, but what I wanted to show you with this slide is that you can apply the same principle for higher orders, like second or third order. So also, I mean, performing second order leakage detection test is slower, of course, and so it grows quadratically with the length of your trace. Third order attacks will grow cubically, and so on. And so that's something that a priori is bad, but it's exactly the same complexity problem that you will face if you are launching DPI attacks. So our tool scales as DPI attack scales. So you could also try to incorporate typical improvements that you do, for example, trace compression or time sample selection, to make faster DPI attacks. So you could incorporate those tricks into these leakage detection tests. So we also applied this tool, or a preliminary version of this tool, to some hardware designs that we did. So this is higher order mask AES that was presented last year by a colleague, Thomas, and other people from our group. And well, we use this tool in the preliminary design phases. So Thomas gives me code, and we test it, and then we decide where to put refreshing blocks, for example, or what to modify in that design. And then, of course, we perform an actual evaluation on an FPGA. I mean, this tool is not meant to replace established methods for performing leakage detection on actual measurement traces or DPI attacks, but it's just something that we use in our design flow to speed up this process. Yeah, so For example, here in this particular case, we figured out where exactly to put refreshing blocks to achieve second order security in this higher order masks AES box. The performance of this tool, so I already talked about how it scales with the order. Performance is, well, you can run it, I run it on my laptop. I don't need a special supercomputer or something like that. Of course, it's highly dependent on how you strip down your masking scheme, but the running times are something that you can, are manageable. There is one important remark that this method is embarrassingly parallel, so it's really easy to parallelize. So contrary to other approaches, if you have 100 computers, then you can run the same thing 100 times faster. It's very easy to parallelize, although I didn't do it yet. So there are many other approaches. So this is not like the first tool that helps you to spot flaws in these masking schemes. Well, in our view, it's a very simple and a very immediate way to do this. In the same way that, well, you can, if you want to write in gravity zero, if you want to write in space, you can either go for a very complex pen or just use a pencil. So that's the pencil approach is what we try to follow in this paper. For example, there is another tool that is by the team of Gilles Barth and others that also, some also other people presented already on Monday. It's the Best Paper Award. I don't know if probably some people are in the audience. So there is one tool that is based on EasyCrypt that essentially outputs proofs whether the masking scheme is flawed or not. So this is really a hard proof. Well, their approach is based on EasyCrypt. And EasyCrypt is a complex and impressive achievement, let's say. And well, last time I checked, it was around 180,000 lines of code of OCaml code. Well, and this is also one point where the approaches diverge a lot. So this is something that will tell you a hard proof. This is something that there is no statistical evidence, but something really consistent. But it's probably a little bit harder to maintain than our approach. So you could implement what I write in the paper in about 700 lines of C++. Okay, so that's some order of magnitude less. So this is almost everything what I wanted to tell you. So we presented a quick method to test if your masking scheme may be okay or not. We don't output proofs. The approach is based on sampling, on statistical sampling and statistical tests. And well, we find it useful, so I hope some of you also do. Thank you very much.